Alright, so this is the, last set of notes, in the beginning of 6.3, we found critical values. Alright, there are 3 ways to do it. You find your first order derivative, set them equal to 0, and it depends on what you're given. So if it's just solve for x, solve for y, you do that. If they're linear, you can plug them into a matrix. If they're not linear, well, then you have to use substitution. Alright, the next step, just like when we did with one variable cases, is to find, are my critical values maximums, minimums, or neither? Alright, and so finding our relative extrema. Alright, just like with the one variable case, there are 2 of these. Remember, in the one variable case, there was the closed domain case, where we can find the critical values based on my criticals or my endpoints. Or there was the open domain case, where I use my second derivative. There's still kind of those 2 cases. The first case we're going to look at here is using the second derivative. So this is more the open case. I have all possible answers on my domain of my function. And we're going to figure it out using what's called the second partials test, or it's also known as the D-test, because there's a D formula that we use to determine if we've got max mins or neither. Alright, so the first step is obviously find the critical values. And so I'm going to kind of walk through an example as I'm giving you this case. Alright, so I've got, first step, find my critical point. So this is an example where I found the critical point. So this f of xy has 3 critical points. There's critical point at -2, 4, 0, 0, and 5, 25. And I had to find my derivative, set them equal to 0. And this one required the substitution method. In case you're curious, I had to solve with the substitution in order to get those answers. Alright, but again, we did critical values on the last set of notes, so this one's focusing on the test for whether or not we've got max, minimums, or neither. Alright, so we need our second derivatives, just like the second derivative test. Well, we've got more than one second derivative. In this case, we actually need 3. We need the second derivative with respect to x twice, second derivative with respect to y twice, and the second derivative with the mix. And you can define either mixed. In this case, again, it doesn't matter, but just to formalize it, we do say x, y, that order, but if you found the other order, it wouldn't be a big deal, it's the same. Alright, so in order to get to the second derivatives, though, I need my first. I'm going to write my first derivatives up here, and then I'll find my second derivatives. Alright, so the first derivative with respect to x is going to come out 12x squared plus 40x minus 4xy. Derivative with respect to y is going to come out 2y minus 2x squared. Alright, so there's my first order derivatives, and now my second order derivatives. Alright, so my second derivative with respect to x twice, my mixed derivative, and then my second derivative with respect to y twice. Alright, with respect to x twice, I'm looking here, and so its derivative is 24x plus 40 minus 4y. Alright, the derivative with respect to x then y, so again, still looking here, derivative with respect to x then y, that's the only y part, and so negative 4x. Alright, now the second derivative with respect to y, so again, I'm using this one. 2y is the only y part, so the second derivative with respect to y is very simple, just 2. Alright, there are the second derivatives that I need, and then what we're going to do with those second derivatives is, the reason why this is also called the D-test is because I actually have a D-test formula we have to set up. Alright, so what I have to do is I have to take my critical values, which we found in step 1, and plug them into this D formula that I have to set up using my second derivatives. Alright, and the way it sets up is it's the second derivative with respect to x times the second derivative with respect to y. Alright, so this is the second derivative with respect to x times the second derivative with respect to y minus the mixed derivative squared. Alright, and so that's a formula you typically have to memorize, but since this is all online. Alright, so I'm going to do it for this case. Alright, so right now I'm just going to write my generic xy. And so the second derivative with respect to x times the second derivative with respect to y minus my mixed derivative squared. Don't forget to square it. That's an easy one to forget. If I'm going to forget something, I'm going to forget to find that in squared. Alright, so I go back up here and I plug in my derivatives. Alright, so the second derivative with respect to x, well, that's that expression, so I plug that in there. So I've got my 24x plus my 40 minus y, minus 4y, times my second derivative with respect to y, which remember that was just 2, minus my mixed derivative, which was negative 4x, but don't forget, it's the negative 4x, the whole thing, squared. I will simplify this because we will eventually use it. Alright, so my D formula for this example, if I distribute my 2, it's going to come out 48x plus 80 minus 8y minus 16x squared, right? When I square negative 4, it comes out 16. When I square x, it's x squared. Alright, so there is the D test that I use for this function, which we will use it in a little bit. Right now, before I go to using it, I'm going to explain how we use it. Alright, so I'm going to kind of hold on to this, and I will come back to it. Alright, this is just an example of showing you it's a formula. When I find my D formula, it's a formula. Alright, so what you do is, well, then you plug your critical values in. Alright, so I'd take this formula, and we're going to eventually do this. You'd plug in your critical values. Alright, when you do, the results are then read the following way. Alright, so if we plug in, so again, this is just in general. If we plug in, so remember, AB is the critical value. Critical point. Alright, so we take the critical point and we plug it into our D formula. If we plug it into the D formula and the value comes out positive, so our D formula comes out positive. Alright, when I plug my critical value in. What that tells me is it tells me it's a turning point. That's what it's telling me. It means it's turning in the same direction in both x and y. That's what it means. That's literally what it means. So it means it's turning the same way with respect to x. It's turning the same way with respect to y. I don't know which way it's turning yet, but I know they're both turning in the same direction, which means it's a maximum or a minimum. But now I've got to see, well, which direction is it turning? And so there's a second part of this test. So if it comes out positive, yes, it's an extrema. I just don't know which one until I check concavity. Right, just like with the first derivative, it still comes down to testing concavity. Alright, so you can either pick, we generalize it by saying the x direction. So if I take my critical value, plug it into the second derivative with respect to x, if I do that and it comes out negative, right? This is, I plugged it into my second derivative and it came out negative. Well, if my second derivative with respect to x is negative, coincidentally also should be the same way for the second derivative with respect to y is also negative. Then it's concave down in both directions. The D says it's moving the same way in both directions. And so I'm concave down in the x direction, I'm concave down in the y direction, and so I have to have this type of shape. So yes, it's a maximum. Alright? If, so this still has to be true, my D formula has to come out positive, but then I plug it into my second derivative with respect to x. If the other outcome comes out, the second derivative with respect to x is positive, coincidentally, so will the second derivative with respect to y is also. That's what the D test is telling me, is they're both moving in the same direction. Right, so what's happening is it's concave up in both directions, and so I'm concave up in the x direction, I'm concave up in the y direction. Well, that means it has to have a bowl-like shape, And so then, yes, it's a minimum. If, all right, so that's if those are the two things that can happen if the D test comes out positive, all right? So I plug my critical value in my D formula, it came out positive, and then check to see, so that means it's turning the same way. If it's turning where it's concave down, maximum. If it's turning where it's concave up, minimum. All right, the third thing that can happen is, remember the neither case. We could have a neither case in a one variable function. Well, we can have a neither case in a two variable function. If I plug so this is again, I'm plugging my critical value into that D formula at the beginning. All right, if the D test is negative, I'm done. What that negative means they're moving in opposite directions. It is neither a max or a min. What we do is, we call it a saddle point. And the reason why is because of the shape comes out. And I'm going to go back to the book to kind of show you, but the reason why is you've got differing concavities. In the x direction, suppose it's concave up, and in the y direction, it's concave down. And so they're messing each other up. So I still have a stopping point. That's still a critical. It stopped, but I didn't turn the same way, and so there is no extrema, and we call it a saddle point. So that critical is called a saddle point. The reason why it's called a saddle point is because that's the shape, the three-dimensional graph. It's a little hard to see here in my two dimensions, so I'm going to go to my book, and the next page over will kind of show you, maybe if it'll go there. There it goes. We'll show you the saddle point shape. All right, and so this is if you look at your book, this is the shape that comes out. And so again, what's happening is I do have a stopping point, but concavity is different in different directions. All right, in the x direction, it's concave up. In the y direction, it's concave down. They're different, and so it's neither a max or min, it's just a stopping point. And so there's a critical value, but it's called a saddle point. All right, so again, that's the shape that comes out. Therefore, and again, they kind of give you a demonstration here with a blanket. It's kind of cool if you look at that. And that's in your book on page 544. And it's explaining how the saddle point looks. All right, so I'm going to go back to our notes. Oops, that's not my notes. There. All right, and look at the example I had before. All right, so for this example, we're going to test 3 critical points using the D formula and seeing if I've got maximums or minimums. All right, so I'm going to rewrite the D formula I found earlier. So the D formula I found earlier was, remember when I took my second derivatives with respect to x, with respect to y, multiplied them out, and subtracted the mixed derivative. It came out 48x plus 80 minus 8y minus 16x squared. All right, so there is my D formula where I'm going to have to test all 3. So I'm going to start off and I'm going to test the 0, 0. Right, so I'm going to take 0, 0 and plug it in my D formula. When I plug 0 in, 0's out, 0's out, 0's out, leaves me with an 80. Well, 80 is a positive, and all that's saying is, yes, it's a extrema, a possible max or min. Max or min. I just don't know which one it is yet. All right, so to figure out, well, is it a max or is it a min, we'll have to check my second derivatives. Concavity. So second derivative with respect to x, which if you remember the second derivative with respect to x was 24x plus 40 minus 4y. I plug my 0, 0 into that. 0's out, comes out positive 40. So positive 40 means it's concave up. If it's concave up, meaning it has that shape, and so that tells me, my test is telling me that this is relative minimum at that value. So at 0, 0, I find a relative minimum. All right, well now I'm going to do the same thing with the other 3 points. All right, so there's 0, 0, and now I'll test the next point. Negative 2, 4 will be the next one I test. All right, so I'm going to erase this so I have room to test it and look at my formula. So give me a second while I erase it. So negative 2, 4 is the next one I'm going to do. plug it in my D formula and see what comes out. Alright, so now I'm going to test -2, +4. So plug my -2, +4 into my D formula. Alright, when you plug all that in, it comes out -112 less than 0, and I'm done. As soon as my D formula comes out less than 0, that means this is a saddle point. Alright, meaning it is neither a max nor a min. Alright, then the last one, I'm going to see if I can squeeze it in down here. So my derivative, or my D test of 525, the 0.525, the last one. Alright, so I'm going to plug that into my formula. Alright, just based on the fact that it's plugged in, this one probably is going to come out -2. It does, -280. So my D came out negative. So I'm done. That means the 0.525 is also a saddle point. Alright, because of how complex multivariable functions are, it's not rare to get saddle points. They actually happen fairly frequently. Alright, and so this is how we test. And so in the next set of notes, we're going to practice that. So we're going to practice finding it, where we have to find the whole thing. Find the critical values, find the D test, and see if we've got maxes or mins. Alright, and so that'll be the next set of notes. So we'll stop that there.